Let's talk about node voltage method and why it works. To make things easier for ourselves, let's consider an example circuit. Let's start by defining a potential function on the circuit. By defining potential function, I mean specifying the voltages at different points on the circuit. It is usually convenient to pick one of the points as a zero voltage. So let's say I pick this voltage as 0. Then according to the definition of the voltage V1, the voltage at this point would be V1. And according to the definition of the voltage source V2, the voltage here would be V2. And let's say the voltage here is Vx. An important implication of defining a potential function on a circuit is that we are saying the voltage drop across all elements in the circuit will be consistent with this potential function. So what do we mean by that? Let's say you're moving a unit charge from the ground node to the center node in this path, like this. According to the definition of the voltage source V1, we need to exert a work of V1 in order to move a charge from bottom to top. And then we need to exert another VR1 amount of work to move the charge particle across the resistance. So the total work done on the charge would be V1 plus VR1 to go from the ground to the center node, right? And according to the definition of the potential function, this work should be equal to Vx minus 0 will be equal to Vx. Now let's say you move the charge particles in this path. According to the definition of the voltage drop across the resistance, you need to exert an amount of VR3 on the charge to move it in that path. And according to the definition of the potential function, this should also be equal to Vx minus 0, which will be equal to Vx. Now, if you subtract these two equations, you get V1, or if you subtract equation 2 from equation 1, you get V1 plus VR1 minus VR3 should be equal to 0. Note that this is precisely the KVL equation across that loop. So what this means is this. By defining a potential function on the circuit and requiring the potential drops across the branches to be consistent with this function, node voltage method automatically ensures that all KVL equations are satisfied. For students who want to think a bit more deeply about this, let's think back to what you learned in calculus. Let's say you define a function f in R2. You then take the gradient of the function. Note that this gradient will be a vector field. And you take the curl of that vector field. You know this should be equal to 0 because curl cross gradient is equal to 0. Now let's see what happens if you integrate the vector field, the gradient of f, along a closed loop C. Using Green's theorem, we know that that should be equal to the surface integral over an area D, where C is the boundary of D, and the surface integral of the curl of the vector field on the right hand side. But we know the curl of a gradient is 0, so the right hand side should be 0. Which means if you take a function and then you take the gradient of that function and you integrate the gradient across any closed loop, and that integral should be equal to 0. This is the same as KVL on circuits. Note that KVL says the sum of voltage drops around any loop is 0. In the continuous form, that means the integral of a gradient of a function across any closed loop is 0. So now let's get back to circuits. We're going to take the same example circuit again, and note that I have already defined the potential function on the circuit. And as we discussed right now, as soon as I define the potential function on the circuit, and while solving the circuit, I'm going to make sure that the potential drops across all the branches are consistent with the potential function I defined. As long as I do that, all KVL equations will be satisfied. So I don't have to worry about KVL equations anymore. I only have to worry about KCl equations. So let me write a KCl equation on node Vx. I'm going to first label the branch currents as shown. And note that the statement of KCl is sum of all currents going into a node is equal to 0. So in this case, that will correspond to this equation here. I'm going to then use Ohm's law to convert these currents in terms of the potential function voltages. I1 will be equal to V1 minus Vx divided by R1 according to Ohm's law, plus I2 would be V2 minus Vx divided by R2, plus I3 would be 0 minus Vx divided by R3, and that will be equal to 0. taking all Vx terms to one side, which implies Vx is equal to the right hand side here. And that's not voltage method. Just to do a brief recap, start by defining a potential function, write Kcl equations, then solve. Note that in this example, I only needed one Kcl equation to solve the entire circuit. If you notice the number of essential nodes in this circuit, there are two essential nodes. One is over here and the other is over here. All the other nodes are not essential nodes. In general, you will need n-1 Kcl equations, where n is the number of essential nodes. So this is my question to you. Why? Think about this. I'll probably post an extra credit question to see how you guys answer this.